Greetings. Let's try to understand the concept of distribution factor. If I want to define the distribution factor, it may be say as when a moment is applied at a joint to create rotation without causing the member to translate, the moment is distributed among all of the members joined at that joint in proportion to their stiffness. The ratio of summative stiffness at the joint to the member stiffness is referred as a distribution factor. For example, let us have a joint here, O, which is connected with n number of members having the stiffness K1, K2, K3, and K4. The ratio of the individual stiffness versus the summative value of the stiffness at the joint is said to be a distribution factor, and this distribution factor depends upon the individual capability of the member. Mathematically, we can say dFi is equals to Ki divided by summation of K, where DFI is nothing but distribution factor of ith joint or ith member at the joint is equals to Ki, the stiffness of that ith member divided by summation of K is the total summative value of stiffness at that particular joint. Since it's a participative contribution of all members, that's why we can say sum of distribution factor along a joint should be equals to 1. They may differ individually based on the material characteristics as well as geometry. Let's try to understand this with reference to a numerical example. For this, I have taken a continuous beam having two span AB, BC, where A joint is fixed, B and C are the hinge joint. Let us say E is constant throughout the member, A is also constant throughout the member, I is also constant throughout the member. The length of member is 4 meter respectively. So if I want to know the distribution factor at the joint B, because I say this is a joint where there is a possible rotation because A is locked. I can't have any rotation to be there because of the locking of the joint. So if I consider the joint B here, we see that there are two members meeting at the joint B, B2A and B2C. I will make a tabular distribution of the values here, which will have n number of columns and n number of rows. The very first column will be related to the joint under construction. So we are having joint B under construction. That's why joint B. Then we will collect all members meeting at that joint. So the members meeting at this joint is BA and BC. Then we'll take the cognizance of length of that members. The length of individual member B2A and B2C is 4 meter, 4 meter. Inertia of that member is given to us, I. Absolute stiffness. Absolute stiffness, we have defined this absolute stiffness is referred in terms of EI by L, where modulus of elasticity is taken in consideration. We have taken 4 EI by L, substituting a value of L here by 4, we get a ratio 4 EI by 4, resulting in a value of EI. Now, how I am writing here 4 EI? For writing this 4 EI, I will go to the joint B and see the far end towards the A, because I am referring the member BA, B to A. I am going to see the far end is fixed. So we know that when far end is fixed, then the stiffness contribution is 4 EI by L. In a similar way, I will go towards the joint B and look towards the far end C. Far end C is hinge. That's why in this case, absolute stiffness is considered as a 3 EI by L. The 3 EI by 4, which comes out to be 0.75 EI. This is the absolute stiffness of the member B to C. Now we'll talk about the joint stiffness. Joint stiffness is nothing but summative value of this absolute stiffness, which will be equals to 1.75 EI. If I add these two particular values, 1I plus 0.75I, it is 1.75 EI. Now we'll talk about the distribution factor. As we say, distribution factor is nothing but ratio of individual stiffness versus the joint stiffness. Here I am going to take a ratio of EI divided by 1.75 EI, which work out to be 0.57. The similar way for the member BC, we have 0.75 EI divided by 1.75 EI, we will get a value 0.43. As we said that distribution factor at a joint should be equals to 1. Addition of distribution factor of all members should be 1. So here if you add this 1.57 and 0.43, we are getting a value as 1. One more example we'll take. Here once again I have considered a continuous beam having two spans. Here joint A and C has been locked and joint B is being hinge support. So if I write the distribution for the joint B, we can again have a tabular distribution of the values here. Very first column will be joint B under consideration, member B to A, B to C. Length of the member are 4 meter, 4 meter. Moment of inertia is constant. That's why I put II here. Absolute stiffness will be equals to 4 EI by L. How I am getting this 4 EI by L? I will go to the joint B and look towards the joint A. Joint A is fixed. That's why the stiffness will be 4 EI by L. Now talk about the member B to C. Now once again, I will go to the joint B and look towards the joint C. C is fixed here. That's why here 4 EI by L I will consider. Then the ratio comes to be EI. Then we have to go for addition of these two values at a joint to get a joint stiffness. Then EI plus EI, it comes to 2 EI. When I work out for a distribution factor, it will be individual stiffness of member divided by joint stiffness. So it will be EI divided by 2 EI, work out to be 0.5. Similar, the member BC will get 0.5 again. If I add the distribution factor at the joint here, from all members, the addition comes to be 1. That's the supportive examples for the description which we have. We'll come up with some more updates with a short discussion. Till then, goodbye, be safe.